What we're going to do today is to use the calculus of variations to study the motion of planets. Right? Why are we doing this? You see, this technique of calculus of variation is actually very important in advanced physics. So what we'll do today is just get a taste of it, right? And see how it can be used to discover laws of physics. Okay, so let's begin. Write our title using calculus of variations, right, to study the motion of planets. Right. Okay. Let me split up the board into two halves. The first half, I would like to use this technique to see how we can actually make discovery of two important laws of physics. In the second half, we'll try to see what kind of orbits the planet will actually follow. Now, firstly, we try to learn about this thing called the Lagrangian, right? Lagrangian, use L to represent it, is actually the difference of the kinetic and potential energy, right, related to the system. Now the kinetic energy is half mv squared, and the potential energy, now here we are going to assume that we already know the inverse square law. So therefore, if we know the inverse square law, we know that the potential energy related to the planet will be negative of some constant over the distance between the planet and the sun, right? Ke minus Pe, right? Ke minus Pe. Kinetic energy minus the potential energy. Now this quantity called the Lagrangian, okay, satisfy another important relation called the Euler-Lagrange equation. Okay, now the Euler-Lagrange equation says that the derivative d dt of the partial derivative of L with respect to Q dot equals to del L over del Q. Okay. Now we use partial derivative because the Lagrangian is actually a function of several variables. You see, although we write Ke as half mv squared, but actually we can decompose it into half m r dot squared plus r theta dot the whole thing squared. That's the Ke. Minus become a plus K over R. So this is the whole Lagrangian. You can see that there are a few variables related to L. First of all, there's R, then you have got R dot, then you have got theta dot, right? Although theta didn't appear, right? Strictly speaking, the Lagrangian is actually a function of four variables: R, R dot, theta, theta dot. So we have to use partial derivative to represent it. So Q is one of the coordinate, either R or theta. Okay? Okay, so let's begin. We're going to do lots of differentiation today. First, let's work with R. Okay, so with R, what do we get? Now, to be carefully, we're going to work with our Lagrangian, which is here, and we're going to differentiate del L over del Q dot, del R dot in our case, and later on differentiate with respect to time. So let's leave the derivative with respect to time outside first, and let's do the del L over del R dot. Now what is R dot? R dot is up here, you see? So when you want to differentiate R dot squared, you get 2R dot. That's a simple derivative, just like when you differentiate x squared, you get 2x, right? So r dot, just treat it like a variable. Okay, differentiate r dot. Differentiate with respect to r dot of this function L. It's just 2 r dot, and there's a half m outside, so cancelling that, you get m r dot. Okay, now I don't have any more r dot, so that's the only one. I can close my bracket for my left hand side. Now I go to the right hand side. Now this time I'm going to do a del L del R. Right, this Q here represents R. So how many R's do I have? I see an R here, I see an R there. So first let's work with this R. Alright, now this is also R squared. Now don't worry about the theta dot squared because we are doing partial derivative. So you're going to treat the theta dot squared as if it's a constant. So we focus on differentiating the R squared here. We'll get a 2R multiplied by the half m outside. I'll get m r theta dot squared. Alright? Now this expression here, k over r, when we differentiate that with respect to r, will give me minus k over r squared. Right, let's call this our first equation. Okay, so we have got m r theta dot squared minus k over r squared for the right hand side, and for the left hand side, I will have to differentiate with respect to time of this expression that was obtained by differentiating Lagrangian with respect to r dot. Right, r dot is just one of the variables. Okay. Now, with respect to theta, we're going to do that also. Now, my Lagrangian, in terms of theta dot, there's only one term here. Alright, so again, by partial derivative, I'm going to keep my r squared constant. I'm going to focus on differentiating my theta dot squared. Differentiating theta dot squared will give me 2 theta dot, and multiplying half m there, I'm just going to get m r squared theta dot. Okay? And on the right hand side, where I need to differentiate with respect to theta, right? Q in this case will be theta. There's nothing for me to differentiate, right? There's no theta at all on my right hand side. There's theta dot, but there's no theta. Unlike just now, we've got r and r dot. So we've got both left and right hand side to work with. Here, it is easy. Nothing, so it's 0. So these are the two Euler-Lagrange equations that I have obtained by working with my Lagrangian representing the planet's energy, right? The Ke and the Pe, right? The planet and the sun system's energy. Okay, now if you look at equation 2, that's the easier one, right? From equation 2, what do we realize? We realize that we have got a quantity whose derivative with respect to time is 0. Okay, now something whose derivative with respect to time is 0 is called a conserved quantity. And what is this quantity? Now, this quantity is called the angular momentum. Right, angular momentum. It has to do with the rotational motion of the planet. Okay. Right. This mr squared is what we call the rotational inertia or moment of inertia. This theta dot squared is the angular velocity. Okay, so we usually use a symbol J, right, to represent angular momentum. So equation 2 actually tells us that we have got conservation of angular momentum. Right? Angular momentum won't change even as the planet moves around the sun. Right? So mr squared theta dot equals to J, which is a constant. Now, if you look carefully, actually this is related to the second law of Kepler. Remember Kepler's law, which is telling us that equal area equal time, right? For a fixed time, you sweep out an area, and that is a constant rate of sweeping out. This is actually that rate of sweeping out the area, right? Or more precisely, it's twice the rate. We used to use h to represent it in our earlier lessons, okay? But here we multiply with a m, and this whole thing is called the angular momentum. It is a constant, right? So nice, we actually derive a law important law in physics, conservation of angular momentum by working with the Lagrangian and the Euler-Lagrange equation. Okay, so that is equation number 2. We already got one useful law. And by the way, I'm going to make good use of this later. So I'm going to box this up because I'm going to use this very, very often in my later derivations. Okay, now equation number 1, that's going to be a bit more complicated. All right. First, let's do a differentiation. Now, this is not too hard because we are differentiating r dot, m is a constant, r dot is dr dt. So if I differentiate again, I get my d2r dt squared, which my notation is to put another dot on top. So I got m r double dot, okay, is equals to m r. Now this is where I'm going to make good use of my theta dot squared. Right? Every time you see a theta dot, try to replace it with j over mr squared. So I've got mr times j over mr squared, the whole thing squared, then minus k over r squared. Okay? Okay, now there's a little trick that we're going to play so as to transform this equation into something that is going to be easier to work with. Right? We're going to multiply, right? Multiply both sides with dr dt. Right? So in other words, I'm going to write it as m r double dot times r dot. Right? Okay, this is to multiply both sides by dr dt. Okay, now why do we do it? Because of this. Now before that, maybe I simplify a little bit on this so that we can see clearer. Now let's simplify this expression a little bit, right? Because if we expand out our m squared here and the m should cancel out our r, and this one will be r4 will simplify to j over mr cubed. Can you see that? Right? Minus k over r squared. Okay. Now, first, observe that this is actually the derivative of an expression with respect to r. Okay, let's call it d of dr. Can you see what is it? You see, if I put j over 2mr squared, right, that really tests your ability to do differentiation. You check. When you differentiate j over 2mr squared, differentiate that with respect to r. Do you get j over mr cubed? Okay, nearly. You need a minus sign here. Okay, because r to the power minus 2. 1 over r squared is r to the power minus 2. So when you bring your minus 2 down, you get a plus 2. The plus 2 will cancel with the denominators 2. Then you get an r cubed at the bottom, and that's exactly j over mr cubed. Whereas the other one, if I differentiate k over r, I'm going to get negative k over r squared. Do you see that? Okay, so when I take this expression and multiply by dr dt, what do you think I will get? Okay, minus j over 2mr squared plus k over r times dr dt. Now, d of something with respect to r times dr dt. By chain rule, that's just d of this whole block with respect to t, isn't it? Right, that's chain rule. Whereas on the left hand side, I'm also going to play a little trick. This is actually the derivative with respect to time of half mr dot squared. So on both sides, therefore, I can write it as derivative with respect to time of negative j over 2mr squared plus k over r, that's my right hand side, and on my right hand side it will be the derivative with respect to time of half mr dot squared. Now let's take a closer look at this. Is it true? Well, we are differentiating with respect to time. We have got r dot squared, which we want to differentiate with respect to time. So first you must differentiate with respect to r dot, that gives you 2 r dot, the 2 and the half will cancel, and you will have your mr dot appearing. Then don't forget you have to finish up with chain rule. differentiate r dot with respect to t, and that's where the r double dot appear. Right? Try to work it out yourself, and you will be able to understand all this differentiation. Now, we're going to shift all the expression to one side, and then we will realize that we have another derivative that is equal to 0. d of dt, we have half mr squared. Now the minus bring over will be plus j over 2mr squared, then minus k over r. Derivative of this equals to 0, just like derivative of this equals to 0. Now that quantity there is called the angular momentum. Could you guess what this quantity will be called? Now observe it carefully. We've got half n r dot squared. R dot is what we call the radial velocity, the speed along the line joining the planet and the sun. This changes with respect to time, the radial distance changes with time, and hence will give you an expression like the kinetic energy related to that radial velocity. This, on the other hand, will give you the kinetic energy related to the tangential velocity of the planet. So together, these two are actually the kinetic energy of the planet. And don't forget, we also have the potential energy, negative k over r. That was the PE, remember? Okay, so half m r dot squared corresponds to this. Wait a minute, I think I missed out a square somewhere. Yes, there's a square up here. When you square this, you should have a square there. And hence, all this I should put a square. Okay, it's good that we discovered that early, huh? Right, of course, here also. J squared over 2mr squared is a little bit like the other term of my KE. So this whole thing is my KE, this is my PE. So you have KE plus PE. Over there we have a KE minus PE. Watch out. Okay? KE plus PE, right? There's minus K over R, there's a plus K over R, so there's no conflict. Right? This is a KE plus PE, and over there is a KE minus PE. It's the total energy that is conserved now. Total energy, let's call it E, that is conserved. So nice. Through the Euler-Lagrange equation that we worked through, we have actually discovered two useful laws of physics in the motion of planets around the sun. Conservation of angular momentum, conservation of total energy. Right, so that's the first part that I would like to go through with you. Now the second part is that we're going to start with this total energy conservation idea and see how we can actually get the motion of the planet, right, the path taken by the planet, work out. Okay, now let's write down E. Half m r dot squared plus j squared over 2m r squared minus k over r is my total energy. I call that E. Okay. Now the first thing I would like to do is to isolate my r dot. Okay. That means I just want to make r dot the subject, right? So if we shift the rest over to right hand side and divide both sides by m over 2, I will get my r dot squared. Okay. So let's work out 2 over m multiplied by E minus j squared over 2mr squared plus k over r. That's my r dot squared, making it the subject. Okay. Maybe let's simplify a little bit by multiply the 2 over m in. So that would be 2e over m. There should be some simplification. That's j squared over m squared r squared. And then plus 2k over mr. Okay, that's my r dot squared. Okay, and if I want to find my r dot, that's just taking a square root. Okay, now we could have taken a positive square root, we could have taken a negative square root. It really doesn't matter. Okay, really doesn't matter, because finally we are going to be able to use either the positive or negative square root to derive the path taken by the planet. So here I want to choose the negative square root. It will be a little bit more convenient for me. Right? So I'm going to choose the negative square root for my r dot. Okay. This whole block, 2e over m minus j squared over m squared over r squared plus 2k over mr. Okay. And then here comes the same old little trick. Remember, this is dr dt. Okay. Now what is dr dt? Dr dt is dr d theta times d theta dt. Right? So dr d theta times d theta dt is theta dot. So j over mr squared is actually this whole block. Okay? It's again that trick with the chain rule, right? dr dt, this is actually dr dt, is actually equals to dr d theta times d theta dt. This whole thing is actually your d theta dt, right? Hope you can see that. Right, it's the chain rule. Now, my aim is to find a relationship between r and theta. These are the only two variables. Okay, these are the only two variables. You can see over here, these are all constants. R is a variable, R is a variable, R is a variable, J is a constant, right? E is a constant, K is some constant. Everything is constant except R and theta. Now how am I going to do it? We're going to use separation of variables in solving this differential equation. Look, you can throw your d theta to the other side, bring this whole square root down, then on one side you only have r and dr, on the other side you only have d theta. Okay, so I'm going to leave my d theta alone, right? Imagine d theta is cross multiplied to the other side, this whole block is brought down, and I'm going to have negative of j over mr squared, alright, divided by this whole block of square root, 2e over m minus j squared over m squared r squared plus 2k over mr dr. Okay, at this stage, if you try to solve this differential equation, is most likely you'll get stuck, right? It's hard to solve. But if we just use a simple substitution, things will clear up by a lot. Now that simple substitution is to let a new variable u be equals to 1 over r. Now once you do that, du is negative 1 over r squared dr. Can you see my negative 1 over r squared dr here? Although there's a j over n, don't worry too much about that, it's just a constant. Negative 1 over r squared dr, that's my du. Now you understand why I want to keep my negative for my square root. It will be convenient. And hence, I can rewrite this equation this way. d theta will be equals to negative 1 over r squared dr, so that's du, over square root. Now I'm going to push the j over m into the square root. In other words, bring j over m down. Another way to look at it is to divide the top and bottom by j over m, push it into the square root. Now that takes quite some algebra, alright, and you have to be really careful. Okay, now see whether we can get this. Alright, if we are really careful, we will find that to be 2me over j squared, okay, minus u squared. Remember what is u? U is 1 over r. And the nice thing is that this whole expression, the j over m, after you divide top and bottom by and push into your square root, the j squared over m squared will be gone, and you have got just 1 over r squared, and that's u. Okay, and then plus 2mk 2mk over j of u. Okay, now do you see what you will get if you integrate both sides? Of course, the left hand side is easy. When you integrate d theta, you just get theta. Okay, plus a constant. But we're going to let that constant be equal to 0, right? To facilitate our reasoning. On the right hand side, can you see what that integral should lead you to? Well, it will lead you to sine inverse, right? Or inverse sine function. But before we can get there, let's do a little bit of completing the square. Okay, we need to do a little bit of completing the square. Now, this is done by putting these two terms, right, the u squared and that 2mk over ju into one complete square. Okay, and that will be, okay, right, I'm going to just write it down. 2me over j squared plus m squared k squared over j4 and minus away a whole block, which is completed square, u minus mk over j, over j, is it j or j squared? 2k over, let me see. When we plug that in, we should get 2k over, oh, sorry, 2k, 2mk over, yeah, I missed out a little j squared here. Yeah. 2mk over j squared u. Okay, so when I complete my square, do the completing the square, I should get u minus mk over j, the whole thing squared. U minus mk over j, the whole thing squared. Now it may look cumbersome, but again, the effort will be worth it. At the end, you will start to see how the energy will be related to the motion. So we're going to integrate. All right, so we're going to ignore those constant of integration because it's all just a matter of how we're going to orientate our axis later on. So if we just choose that axis of my eventual ellipse to be along the major and minor axis, then I don't have to worry about that constant of integration for my theta, right? Just treat it to be 0. So theta will be, and I said that will be the sine inverse function, right? So sine inverse of this whole block, u minus mk over j, right, divided by the square root of this whole block, square root of 2me over j squared plus m squared k squared over j4. Okay, now just one last thing to do, which is to change u to 1 over r. We will be able to get our relationship between r and theta. Okay, now it takes quite some algebra in terms of the manipulation, right? So I'm just gonna write down the final answer. You can do the algebraic manipulation. Remember that u is equals to 1 over r, therefore r is 1 over u. Take sine on both sides, and you should be able to get a final expression r in terms of theta this way. Right? I'm just going to give you the answer. J squared over mk will appear on the numerator, and the denominator will be 1 plus square root of 1 plus 2ej squared over nk squared. 2ej squared over nk squared, then multiplied by sine theta. Now, this is our relationship between r and theta. Okay, this is our relationship between r and theta. And this form, which relates r and theta, is a form where we see it in what we call conic sections. Conic sections means the study of parabola, hyperbola, circles, ellipse, right? So normally in conic sections, things are written this way, right? ED 1 plus E sine theta, where E is that eccentricity, okay? D is the distance between the focal point and the directrix, okay? And R and theta, one having to do with the distance between the planet and the sun, the other having to do with the angle the line between the planet and the sun makes with the horizontal. Okay, that's the meaning of this. This is actually a conic section. Conic sections. So we realize that our E is actually this quantity here. This is my E, and this quantity up here is actually my ED. Right? You can relate. Right? ED is the numerator, and E is that square root. So accordingly, we can therefore say that E squared is 1 plus 2EJ squared over NK squared. Now comes several interesting properties or interesting results that relates the energy with the eccentricity. Okay, so depending on whether that planet or even comet or whatever body that come around the sun, okay, depending on its energy, it will follow different type of path. Okay, now first of all, when your E is equals to 1, now when E is equals to 1 means that big E is energy, small e is eccentricity. So when the small e, eccentricity, is equals to 1, we know that the energy of the body, all right, the planet or the comet or any other bodies that move around the sun will be equals to 0, right? Because this is equals to 1, this must be 0. And this is a parabola. We have a parabola. Okay? Now next, when E is equals to 0, right? That means there's no eccentricity. No eccentricity. Eccentricity 0 means you get a circle. So that means that the E here must be a negative number. The E here is negative mk squared over 2j squared. And that's a circle. Alright? And what happens if you have E that is more than 1? Well, when E is more than 1, this must be a positive quantity, so we can conclude that the energy is a positive number, and that will give us a hyperbola. Alright, now one last case. So far we have seen parabola, circle, hyperbola. The last case is our ellipse, right? We have been studying ellipse a lot, right, previously. So when do you get ellipse? You get ellipse when the eccentricity is still greater than 0, but less than 1. Okay? So in other words, this total energy here, right? Maybe I will use the space here. I already have very little real estate already. Okay? My E will be a negative number, but it has to be greater than that one corresponding to the parabola, the circle, negative mk squared over 2j squared. And that will be my ellipse. Okay? So, starting with the Lagrangian, right, using the Euler-Lagrange equation, we discovered two important laws of physics: conservation of momentum, conservation of energy. Now, starting with that conservation of energy relation, right, we go through some manipulation, right, to get to a differential equation that we can solve, and hence we finally found a conic sections as our solution. And according to what the energy of that planet or comet or whatever that comes around the sun. It may follow a parabola, a circle, a hyperbola, or finally an